show us that there are many ways in which science can happen. We've talked a little bit about, I've introduced the idea of the fourth paradigm already. Some pundits, even some respectable scientists, have mooted the idea that this is the end of theory, the end of Einstein. We won't need Einstein anymore to tell us what our theories might be. If we have enough data, theory will emerge. But the problem is that learning theory is very difficult. It's a lot different from learning to predict an outcome from a model based on learning a pattern in data. Theory is not pattern. Theory is much more complicated than just fitting a function to a set of data points. So in this talk, I'm going to explore the potential of coupling a new field in computer science, that of computational model discovery, with the process of science as it's practiced in geography and GIScience. So we're going to look at some of the possibilities now, but also what remains to be done. Explanation is, to some extent, a large extent, I think, the holy grail of artificial intelligence. It's one of the long-standing goals, is to create machines that can learn and can reason and can explain. This goal has proven difficult, and we're taking far longer to realize it than was first envisioned when the potential to solve this problem was first postulated. But in the meantime, AI has fragmented into many subdisciplines, such as machine vision, machine learning, description logics, ontologies. All these have addressed specific aspects of the goal of machines that can explain, but they've concentrated less on the big picture. There's been good success in learning when the problem is very specific and there's good example data available. But reasoning is still a major challenge. And although many logical reasoners have been developed, they are often for very specific classes of problems, like how to play chess or Go, which AI is now better at than humans. But explanation has received perhaps the least attention because it's the most complicated. So we're going to look today at how we move from machines that simply predict things to machines that can explain things. And the problem is that all of this fantastic work that's going on in machine learning and deep learning in particular has given us really excellent predictors, which are absolutely terrible explainers. The little highlight in that picture that shows a transfer function between layers of a neural network gives you an insight into what the explanation is that this particular kind of tool provides. If you were to say it explained anything at all, then it explains how one data layer maps to another via a series of these transfer functions. And a typical deep learning network might have hundreds of thousands of these transfer functions, even millions. That's not really an explanation in any sense that a human can make use of it. So this kind of tool and this kind of approach is not going to lead us to insights from a theoretical point of view. It's just going to lead us to good predictions. Now, good predictions are great, but that's not all we want in order to push forward the frontiers of science. We've always been learning from data forever. It's not a new idea, it's where theory comes from. And it's worth dwelling on how computational model discovery differs from the more established data mining and knowledge discovery, which is a discipline we've become a little bit more comfortable with over the last, say, 20 years or so, and perhaps building on the work of people like Stan Openshaw. So generally speaking, data mining and knowledge discovery are good at learning predictive models from data. And they use decision rules or hyperplanes or statistical functions as their building blocks. But they don't emphasize model comprehensibility to humans. nor do they take advantage of any prior knowledge that might be available in a domain. And they produce predictive models that are difficult to connect with existing knowledge and theory. By contrast, what we're after, and what I think computational model discovery aims to deliver, are models that also learn from data, but they focus instead on the interpretability of those models by humans. So instead of using transfer functions, they use equations and constraints and constant and laws as the building blocks for these explanations. So we're assuming here that a human expert who is used to expressing a domain using equations can understand the equations that a machine might generate in order, again, to describe what's happening in a particular model. So we move closer to explanations by connecting observations to theory. There's still somewhat of a cognitive task for the user, for the geographer here, but the model should be explainable as a set of equations that should be familiar to a domain expert. At the moment, when we model, we have to choose one: predict or explain. So we can choose to build a model based on equations and theory that's understood by a community in a particular domain, or we can choose to predict and use perhaps machine learning tools. We can often find that our predictions and our learned models might be better than our explanations, because they tend to model the data more accurately than perhaps the assumptions of a simple model. But they are very poor at helping us explain how we think something works, or even to communicate that explanation to others. Given enough computing power, though, perhaps instead of assembling hyperplanes and transfer functions, perhaps instead we could start trying to assemble millions of different equations together from their constituent parts, then weed out the ones that are poor at predicting model outcomes. We could then refine the better ones until we have equations that really do predict well, but also explain what's happening in a particular domain. So what we're about here is moving the representation of a model away from hyperplanes and towards some kind of mathematical form that experts might be familiar with. So in building a model, instead of moving hyperplanes around, what we're going to try and do is build fragments into useful equations. You could say then, and Judea Pearl in fact did, that all our impressive achievements to date amount to just fitting a curve to data. And when you think of just how good some of our deep learning tools are now, that's quite a humbling statement. All they're really doing is learning to fit a curve. They're not explaining anything. Another statement that I really like here is by Peter Norvig, another famous thinker in artificial intelligence, who says perhaps we should stop acting as if our goal is to author extremely elegant theories, and instead embrace complexity and make use of the best ally we have, the unreasonable effectiveness of data. Because if nothing else, what deep learning has shown us is that data can be extremely effective in predicting outcomes, in helping us predict really complex models from massive and unwieldy piles of data. Just a reminder, in case you need it, that there are paradigms in science, and this data-driven idea of data-driven science has been called the fourth paradigm, and that that's because we have three other paradigms that are generally recognized below that. Right at the beginning, we have the experimental paradigm, where because we have standardized on weights and measurements and ways of recording them, units for measuring things, we can repeat experiments about the boiling point of water or the periodicity of the pendulum. The second paradigm of science, which is really well exemplified by Einstein, is the fact that we can be led by theory. Excuse me, led by theory. And we don't necessarily need data in order to be led by theory, but we can use data. Theoretical science posits a model and organizes our thoughts around that model, and usually that's expressed mathematically. Rate equations are the most popular kind of models used there in science. The third kind of paradigm in science is this idea that we can now simulate pretty much everything inside of our computers. And so this third paradigm involves computational modeling, in silico modeling of really complex phenomena in the world, like modeling the climate or modeling global circulation patterns in oceans, or modeling the spread of infectious diseases over time. And because these experiments are conducted in silico, we can conduct millions of them and fitting them to data and experimenting with what-if scenarios. But this fourth paradigm says we don't need to have humans necessarily to lead the production of that theory. Perhaps it can be discovered from the data itself. GIScience, to my mind, is dangerously stuck in that second paradigm. I think actually we are continually searching for more theory as a way to justify our domain. And this is a topic perhaps for another day. But as Norvig suggests, this is not the only way we might move forward. Excuse me. These paradigms in science work best when they work together. So we're not imagining, excuse me, the air conditioning is really cold in here. It's a hot day. It's making me cough. The paradigms in science support each other. They work best when they work together. So nobody is suggesting that the only science from now on would be fourth paradigm science. This nice diagram here from the Sandia group show us how the various aspects, various paradigms of science work together. And each of those paradigms in science actually emphasize a different kind of reasoning. And you can understand how the paradigm works and what its limitations might be by understanding the kinds of inference that paradigm supports. So a lot of what happens in the first paradigm in science is deductive modeling. And in the second paradigm of science, we're trying to come up with a theory that we might use. And that might involve abduction on our part. That is reasoning from effect, data, to cause, explanation. We see some data and we hypothesize a model for how those outcomes might be being produced in that particular system. So this is also called explanation, the art of abductive reasoning, and it's where humans excel. To do abductive reasoning well, you have to know a lot about a particular domain. You have to be familiar with its concepts, with its trends, with its language, with its mathematics, with its findings. And because you're familiar with it, you can hypothesize explanations for things. Any good expert in any field can do this, but it involves a lifetime of study and training and introspection. And machines generally don't carry around with them all the theory of a domain, of an expert area of scholarly inquiry. So they don't have the tools or the language that we have to try and build models. So for machines to do abductive reasoning, they need to know much more than data and equations. They need to know valid ways of fitting these together. They need to have some theory to build upon. And that's, I think, where the next revolution in science will come, not just by analyzing data for patterns, but by connecting this data into conceptual models of scientific domains. So moving from induction using machines, which is what we're basically doing at the moment, learning patterns, to abduction, reasoning about what might be causing those patterns, that's a very big step and a huge challenge. Of course, there are other ways to look at the scientific method, and I found this little diagram in New Scientist recently. It probably represents more truthfully the way we think about science when we do it. We make observations, we form hypotheses, we make predictions, we test the predictions, we get excited about publishing the results, we think about gloating to our rivals or getting a Nobel Prize, or doing a little dance when we're successful, or having a tantrum and sulking when we're not. That's really how we work as humans. So perhaps before we go on, we should think for a moment about what are explanations. A scientific explanation can be described as a set of equations using differential or algebraic form. There might be one of them, or there might be several of them linked together. There'd be rules, laws, and constraints, constants, observed variables such as data, some of which might be results or outcomes that we're interested in. And there might be some unobserved variables or states within the model too. So if we want to build an explanation, then we have to build a mathematical model, a set of, say, partial differential equations or PDEs, that not only characterizes a phenomena of interest, but could be used as the basis of an explanation. So computational model discovery or discovery informatics is a fairly new field. It's been around for probably about 15, 20 years, but it hasn't had much success until quite recently. Pat Langley, a colleague of mine, famous in AI in the USA, who I've worked with a little bit, was perhaps the first person to really try to build systems that could make discoveries and explain them. And in 2002, he built a system that managed to infer the law of gravity from data. Well, that's great, but it's actually a very, very simple model. We need systems that will scale to finding much more complex models from much more complicated data, and that's proven to be very difficult. But as I said a moment ago, we've had some good progress recently. So an explanation specifies a causal relationship between one or more input and output variables via this kind of hidden state of all these different equations working together. So there are 4 steps in discovering a process model that might be described in this way. The first is we need data. We gather relevant data from a domain, and we add in some domain knowledge in the form of equation types, templates for equations, perhaps with rate terms missing, and various other constraints that might be useful in a particular domain. And then the second step is a structural search, where we combine these fragments of equations together using whatever constraints apply in a particular discipline to limit the search. So we're essentially creating a lot of fragments of mathematics to see any of them have any explanatory power. We also need at the same time perhaps to try to plug in the right parameters to these equations too. So as well as searching for structure, we're also doing a sweep over a parameter space, plugging in different parameters into these equations to see if that makes them any better or not, and searching for a good parameterization of an equation. We might get many models produced as a result of running this kind of search. And then, of course, we need a ranking mechanism that can decide which one is the best or fits our needs the best. Now, of course, this is a very expensive thing to do, to search through solutions of fragments of equations. But given the computing power we have at our disposal these days, it's not beyond us. To give an example, this is a simple predator-prey model common in ecology. The predator and the prey have a relationship to each other that's described by a series of equations posited by a guy called Holling in the 1950s. And there are families of equations that describe the relationships between a predator and a prey with a whole bunch of variable terms that need to be instantiated and tuned to model specific instances. What we are trying to do then is to infer from Holling's equations a model that describes a particular relationship between a particular predator and a particular prey, which involves finding the right bits of equation, substituting in the right terms, and linking them together in the right way in order to predict some outcome. So a typical simple model might look like this one here. And this is from work by Bridewell and colleagues, including Pat Langley, who I mentioned a moment ago, who built a system that could automatically generate such models from fairly simple processes in ecology. This is showing you the outcome of such a process. Now, here we can see both the original input data and the model that the system has learned. This is the model that has been learned down here. That's been learned simply by observing the data, by starting with those equations and then synthesizing an equation that fits the data. And the pink here and the green are the output from the model after the system has been learned. And you can see that it's learned to predict the behavior of that closed system pretty well. But if you were an ecologist, you could also remark on how explainable, how understandable that model is, because it explains what's happening between those two organisms in a language that would be very familiar to an ecologist. It's produced equations that they would immediately recognize the form of and feel comfortable with and be able to share with other ecologists. So that is definitely a step forward. But the other step forward that's happened recently is we can now build models that will scale to very complicated systems. This is an example of a graph by a PhD student that Pat Langley and I supervised a few years ago, which shows a learned ecological model with 15 dependent variables. In other words, it's an ecosystem of 15 organisms, 15 sets of complex and lagged codependencies between organisms. And we could discover this model, which is also quite accurate, in a few minutes, given the outcomes observed in an ecosystem. And that I think is quite substantial, moving beyond simple two organism systems to describing the complex interrelationship in a rich ecosystem, which would be quite difficult for humans to do. So small numbers of equations are easy. Larger numbers have taken some time, and there's some clever optimization that goes on behind the scenes in models like this that I don't really have time to talk about now. Be happy to at another day. But this approach scales as you keep adding variables or new organisms into the model. It scales sort of linearly with that, and it manages to do that because it uses strong typing of inputs and outputs in equations, and also strong typing as of methods in terms of the semantics of the domain. It knows something about which fragments of domain might connect together. And so it doesn't make stupid choices. And that narrows down the search space quite dramatically. Also, if we initialize the search for solutions in multiple places, starting with different fragments of equations all over the place, and that we prune the poorly performing ones early, that also helps improve the efficiency of the algorithm. Now, if your domain is very mathematical and there's no distance, if you like, cognitively between equations and your theory, and you could say, well, that probably is done. It's all over. The machine is now inferring theory from data. But in actual fact, that's not really true in most domains, in any domains really. Explanations need to do more than simply connect together equations. They need to show how those equations relate to concepts that are understood in a particular domain, how they relate to current theory, how they function within our current ontologies and epistemologies. So there's a lot of background knowledge that goes into making an explanation. John Sower described this as knowledge soup. Knowledge soup is all the background bits of theory and data and bits of mathematics and constraints that help us to create understanding from what we observe. This includes how does data become knowledge in a particular domain, how its epistemology works, how we establish if something is true, how concepts and ideas change over time and what triggers these changes. All of these are things that help to change the mathematics into concepts that our theories are based on. So we might know something about these ideas in ontology and epistemology and conceptual modeling. And if we can use those ideas to anchor our mathematics, then it becomes more strong, and it also becomes easier to explain what we're doing to other people, and for them to understand our own research, because it's not just mathematics now, but it's explanations of that mathematics couched in our particular field. That's very important. David Harvey, in his book on geographical explanations in 1969, recognized some of the ingredients of knowledge soup from which geographical explanations are made. What I've been doing is combining Harvey's understanding with the understanding from Bridewell's work on inductive process modeling. He's the guy whose results I showed you earlier. So given that we have a model of the research process itself, a meta model of how GIScience might work, and a conceptual model of the domain describing how entities are related to each other, and a set of observations, and a set of generic processes or equations that describe mathematical relationships, and some constants and constraints that indicate plausible relationships, then our task is to find a specific process model and associated parameterization that predicts outcomes and describes how those predictions are made. That's our task. In order to do that, we have to express a process model, equations, as domain theory. And that is a new challenge. It's one, again, that AI is currently working on. Equations need semantics to connect them with key concepts within a domain. These concepts need to fit together within a valid model of the research process. This is a branch of AI that's now called narrative science. Narrative science is the science of taking equations and data and background knowledge and weaving them together into some kind of narrative. You can already see this being pursued in areas such as sports journalism and in some branches of data science in business. So some of the sports reporting news feeds are now written by computers using narrative science based on background knowledge about a sports domain, and the results as are currently coming in over the wire, as it were, and automatically generating a textual narrative from those that humans find appealing. And in fact, we've got so good at this that humans can't really tell the difference between a machine writing and a human writing when it comes to producing that narrative. But what we need to do is to go further and create narratives that connect our scientific explanations and our scientific data to the concepts of our domain. There's an example there of a system that creates narratives from data. I don't have time to show it you, but it is a live demo there at the bottom. The data that you see in the graph there was what was provided as an input, and the text below it is a narrative that's produced automatically from that graph, and it sees all kinds of different insights. So already used in business analytics and sports journalism. We're already beginning to see a similar kind of narrative generation being used in academia. Not in generating words so much, but as generating computational code. There are now some fairly elaborate systems that can generate computational code from mathematical equations. If you can generate code from equations, you only have to describe your model once using equations. You don't have to worry about whether you have mapped or translated the equations into code correctly, because the system does that for you. A good example of that is a journal called Physiome, which is in the bioengineering realm, which uses a modeling language as part of its journal, part of the journal infrastructure, that automatically can produce code from equations. So if you put equations in a paper, then those equations can be automatically translated into computer programs and run by anyone in that community. So in this particular community around this journal, Physiome, the community can submit equations that become code that everyone can run. So if you like, there's a system of AI behind the equations that generate computational code from them, rather like producing narratives. To give an example, here's an article. Here are some of the equations used in that article. This is generated code that uses that article, and the code can be generated in various different language. And here is a runtime of that code with the outcomes visualized. So there is no inertia and an entirely hidden process between the article itself and a running visualization of the mathematics that the author has used. Everything in between those two has been provided in a kind of seamless way. So how close are we? If we want to make a model of the science process that includes theory and that evolves to take account of new theory, how close did we get? Well, equations are not scientific theory, and we still need to do some work to make them interpretable by humans. And it's difficult to connect the process of automated discovery of equations to the conceptual aspects of science. And if we can't access appropriate data, then we'll never see valid signals in the first place. So our models will be either uninteresting or worse, misleading. And discoveries that rely on search methodologies to find candidate models can also find less than optimal models in some circumstances. So there are some caveats around how good the science is, but we can, and also we can only discover explanations based on the forms of provided equations. If there's no template for an equation, it won't be used to try and find a model. But with these comprehensive libraries of equations and with rich data, real discoveries can be made. So there's some truth in the notion of fourth paradigm science. We could hope to move from rich data to rich explanatory models based on equations without the need for human intervention, whether or not that might be a good thing. But getting explanations of those models, it still requires the human in the loop. There is, I think, though, increasingly a smaller gap between the outcome of such a model and a narrative that we might produce. Perhaps you can imagine as a final point, just in your head, imagine where we might go to next. If we can create a automatically running model from the equations in a paper, if we also used some of those ideas from narrative science, we could also have paragraphs of the paper that were produced automatically from the outcomes of models. So we could write a paragraph describing the results that rewrites itself if the results change, and have a live and permanent link between the data, the equations, the code, and the journal article. So that if someone came along and improved the equations or improve the model, the journal article could version itself and then run a new version of itself and then rewrite the paragraph automatically about the results using the new version of the model. Or perhaps better data becomes available and the system simply knows that it's connected back to a data set that's changed, and so reruns itself and produces new results and then rewrites its own text to describe those results better, perhaps changing a negative result into a positive result or vice versa, because the data have changed. So I think the future for us here is live journals that connect our data and our theory and our prose and our narratives all together into a single environment. That's our goal, not a fractured environment where the data is here and the ontology is there and our equations are here and our conceptual understanding is there, but a single environment that weaves them all together so that there's as little distance as possible between all those different ways of expressing and communicating our science. So that's it. That's all I wanted to say for today. There is more in the paper. So that's the end. I'll happily take questions. I put some sample questions up for you up there in case you're feeling shy or having trouble thinking of some. Thanks very much for your attention. I hope there's someone here to ask some questions now. May, I think that would be down to you to try and unmute people. As you do that, I'll make one final comment, and that is one of the things that I love about GIScience and geography is that as a discipline, we have real engagement with the conceptual and the philosophical, as well as the practical and mathematical. We know, most of us do, what ontology and epistemology are, and we may have even paused to think about the roles these play in our own research. I think that actually puts us in a driving seat. Most other sciences are quite ignorant or choose to ignore their ontology and epistemology. They don't agonize over it as we do, and we have our colleagues in critical geography to thank for that, I think. But because we do, we're in a good position to model and represent these ideas in our systems. And in fact, there's been much work in GIScience to try and do so, to model ontologies and the research process as conceptual artifacts. But what we need to do now is to connect them to our data and our methods. Thanks. May, can you hear me?
Hello, this is Mir. I think we can ourselves unmute. The ones who want to ask questions, I think we can unmute ourselves.
Great. Please do ask questions.
Hello, Mark.
Hi.
How you doing? It's Sean Ahern.
Hey, Sean. Good to hear you.
Good. Hey, great talk. Thanks for taking our nose off the grindstone and into this sort of meta awareness space, which is really important. Fabulous timing on this paper and talk. So I've been looking at the COVID-19 and modeling it, and one of the interesting developments early on was the IJME group at the University of Washington was using a data-driven model that ended up being pretty wildly off the mark in terms of prediction. And it was actually used by the Trump administration at the time to minimize the future of the virus's trajectory. And interestingly, they did move to a classic epidemiological model called the SIER model, or susceptible, infected, and removed. This is a process-based model, and the important thing about process-based models is they sort of constrain what's possible.
Exactly.
Whereas a data-driven model can sort of crank out of control and underestimate or grossly overestimate the phenomena because there aren't constraints based on the ecology. So I'd just like you to comment on that in the context of your talk, please.
Thank you. That's exactly the observation I was hoping for. Machine learning operates only in the domain of patterns of data. It doesn't understand how that data might be anchored into reality in any way. And if it infers anything about that, it infers it only from the pattern of the data that's available to it at the time, not from anything that we understand already. So it's not able to use any of our understanding that's captured in equation forms that we're currently familiar with, like rate equations in epidemiological models. So if you can build an explanation system that uses as its atoms rate equations or some kind of partial differential equations, then you are guaranteed that it will be anchored into reality in the same way as any other model that used those equations would be. And so there's a double advantage to this. The first is that we're able to build on existing theory and use the forms of such equations to build elaborate models to suit particular circumstances. The second is that it's quicker to search for models because the equations themselves constrain what's feasible, other than searching in an abstract space using hyperplanes. We're searching in a constrained space of known PDEs. So using process-based representations is far more useful in terms of minimizing errors and maximizing explainability than just simply using hyperplanes or similar.
Well, thank you, Mark. I hope you guys can hear me now. I somehow got muted. We have two more questions that, from the audience. Piotr Jankowski first, then Mir Adolfazi Mostafazi next. So Piotr?
Thank you. And thank you, Mark, for this very interesting talk and for the paper, which I found quite thought-provoking. I'd like to ask you to help me understand the bit of a conundrum that I see in this discovery process that you've presented. So as far as I understand, we start with bits of knowledge, as you called it, little domain knowledge, and we back it up with data. And then in this process, we qualify these, well, we string up these bits of atomic bits of knowledge represented by equations into models. We use the data to verify the fitness of our proposition of a model, and then we toss it, or we keep it, or grow it.
Right.
Assuming that we toss it, we need to go back to our knowledge base and get other bits and pieces of knowledge and put them into a model. And so this, to me, is driven by a hypothesis. And that hypothesis can only, as far as I can tell, be formulated by a human being, not a machine. So a human being is an indispensable component of that entire discovery process. Is my understanding correct, or am I misrepresenting?
Well, I think your understanding is probably still largely correct, but I think this is the challenge of trying to discover models computationally. You are right that every time we connect bits of equations together, those fragments form a hypothesis. And it perhaps takes an expert human to produce a good hypothesis. But a machine can produce a million hypotheses and test them in as much time as a human can construct one. So when that hypothesis gets complex, like how 15 different organisms in an ecosystem codepend on each other, then having some help from a computer to try and fit a good hypothesis through that data might be very useful. And I'm sure that what computational model discovery has already shown is that computers can indeed discover good hypotheses. And in fact, they have also used these hypotheses to make useful discoveries about predictive models in the fields of ecology and in drug discovery. So these tools are just beginning to be used. And yes, they do produce hypotheses. And yes, these hypotheses are as good or better in some cases than the ones humans might make. So I think our days as being the only life form on Earth that can produce hypotheses if a hypothesis is the set of equations, I think our days are numbered.
Right, thanks.
So, Mike, this is Mir from Université Laval in Quebec City. Thank you very much for your very interesting talk. My question is about, actually, maybe I will combine my question to one of or several of your questions in this slide and say that, okay, since we work on GIS science, we always were concerned with uncertainty in data and equations. And so this, my first part of the question, how you would put this uncertainty in this whole process, which is done in artificial intelligence, considered in the way it processes it. And also the starting point where we put, okay, we tell the computer what are our set of possibilities of equations or set of data. So it's us who decide for the computer, this is our data and this is our set of equations. So to which extent, so yes, they can make hypotheses, a lot of hypotheses, but at the end, it's us who tells them the possibilities. Is that right?
Yes, look, those are both really phenomenal points. Thank you for sharing those. I haven't thought at all about how uncertainty is modeled through that process. But I've mentioned just as an aside that if it's modeled in the equations that are being assembled, then it can be propagated through the model in the way you would now. But I haven't thought about any specific enhancements that might need to be made. But your second point is what I'd like to comment on, if I may, and that is that, yes, someone has to choose effective data to share with the computer. And if the signals of interesting models aren't in the data, then obviously the computer can't find them. And the computer can only construct new explanations using fragments of equations and bits of theory that we choose to provide in advance. You're quite right. And I have thought about this. And what I'd imagine is that we might build systems which have a bucket of equations that are normally used in a discipline, but then another bucket of equations that aren't normally used in our discipline, but are nonetheless available to the model. So perhaps what the model could do is spend time trying to build explanations based on equations that are familiar in our discipline. But if it should fail, perhaps start looking at equations that wouldn't normally be used in our discipline, perhaps that come from other disciplines like, I don't know, cosmology. I think many of the best ideas in science come when someone takes a bit of theory from one discipline and then tries to make it work in another discipline. They're reasoned by analogy from I don't know, from cosmology into genetics. And I think we have a real opportunity to try to build systems that can dip into theory outside of our own theory base and see if it helps. Therefore, perhaps making discoveries that we wouldn't necessarily have predicted.
Okay, thank you. Thank you very much for sharing your ideas.
I think, hi Mark, Nenad here.
Hello. Who is this?
Nenad from RMIT University. I think we met last year at the conference, at Geocomputation conference. So I have actually two questions. First question is in regards of explanations. I mean, here in your presentation, you showed us graphs, so how the 15 variables interact, for example. So is there any other form of showing these explanations? And my second question is, are you working on any similar project at the moment, like similar which you done with the PhD student Adam and Peter Langley? Thank you.
Yes. Yeah, those are both really good questions too. The first question is probably my fault for not explaining that well. But the idea behind trying to get beyond mathematical explanations, is that if a system knows that a particular equation, when it's used, if that implies a certain theory about the relationship between, let's say, two organisms or an organism and its landscape, then we can invoke that theory and we can rewrite that equation, or the graph that represents that equation, we can rewrite it as a narrative. So whereas I showed you a graph and I could have shown you a set of equations, what I'd like also to be able to show you, but it's not been done yet, is how that could be translated into a narrative. Now, if we know that an equation represents a predator-prey process or a process of grazing on a landscape and using up resources in that landscape, then we could write what that equation means in prose, in text. We could write a paragraph that describes what that equation means in the language of that discipline, invoking its concepts, not just invoking its mathematics. So I think that's really what I was trying to say, in terms of we can go beyond equations and graphs, but we could actually write narratives of what those graphs and those equations mean in the prose that you might find in a research article. So it might also be possible to write paragraphs of research articles from equations too, because the relationship between those equations and concepts in a domain is actually understood. We as experts understand it. It's just that computers don't yet have a good model of that. Does that help explain maybe that missing piece?
Yep, for sure. I was also maybe referring, were you thinking a little bit in terms of also showing how the process is generated, like using scientific workflows or something like that?
Yes, absolutely.
Would that help, or?
I think so. There's been quite a lot of work on using semantics in scientific workflows, and I think they do provide a useful way of coupling bits of models together, because you can put semantic constraints around strongly typing the equations or the statistical type of the data that's going in and out of those equations. And that can also help you choose valid models and not assemble models that don't make semantic or syntactic sense. So I think workflows might help, yes. And to answer your second question, are we doing anything in this area right now? Yes. We've just begun a project which is looking at how you might write narratives from models. So our long-term goal, and it will take us several years, we just got a big funded project to look at this problem over 7 years. The goal of which is to create the live science journals that I talked about at the end of my talk. Can you create an article that basically writes itself and updates itself from data from which theories are discovered and from which models are inferred, and it keeps itself live over time as models are refined and as new data comes online.
Okay,
but don't ask me for any results next year, because it will take a bit longer than that.
Okay, no problem. Thanks.
Yes. Well, thank you, Mark. Thank you for the interesting presentation, and thanks for all the very insightful questions that expanded Mark's presentation. And in the interest of time, I'm sorry, we have to end it here. In the physical environment, we will give a round of applause for Mark, but right now we probably just don't. Just have me represent all the audience. Thank Mark for the interesting presentation and give us a lot of food for thought. We are planning for the next 2 IJGIS webinars. In February, we will have GeoAI, and in March, Real-Time GIS and Smart Cities. Once the authors have confirmed the dates and times, I will make announcements. Meanwhile, both papers are free access at IJGIS website. I hope that you have a chance to read the papers before the webinars and come share with us your thoughts. at the webinars. Until then, stay healthy and enjoy GIScience.